Hi, folks. So far, in terms of operating on vectors, we've seen how to add and subtract, whether we're dealing with vectors defined geometrically or algebraically. Okay, and we also saw how we could multiply a vector by scalar. What we haven't seen yet is this idea of multiplying two vectors. So what does it mean to multiply two vectors? Okay, and there isn't necessarily an obvious way to do this. So remember, though, that when we're trying to define something new, there's two conditions we usually like to meet. Well, the first one is essential. It can't contradict anything that came before it. And the other thing when we're defining something new is we'd like it to be useful. So I'm going to define a way to take the product of two vectors. Okay, that might seem a little surprising, but what we're going to see is that there is a usefulness to it. Okay, so what we're going to define is what's called the dot product. Okay, sometimes also called the scalar product, and I think you'll see in a second why we call it the scalar product. All right, now when we say we don't want it to contradict anything that came before, even better is if it can still make sense in terms of how we define, say, the idea of product in other circumstances. In particular, like we've done a lot, is we go back to R1, where we go back to the number line, just working with real numbers. So whatever I define this product to be in 2D, 3D, all right, I would like it to still be valid in 2D, meaning if I take, 2 and I multiply it by 3, that I'm still going to get 6. That 2 times 3 is going to be equal to 6, and say I do 2 times negative 3, that'll still be equal to negative 6. All right? And in fact, we're going to use kind of this idea of 1D as an inspiration for it. So if I think of 2 and 3 as vectors, so I take vector 2 as opposed to number 2, and I take vector 3, okay, as opposed to the number 3, when I multiply them, I expect to get 6, okay? Whereas if I take 2, oops, a little long there, if I take 2 and I multiply it by negative 3, I expect to get negative 6 as my final result. Now, by the way, if you're asking yourself, why am I not putting vector symbols here? Well, you'll see in a second, okay? And when we were determining the sign of this product, all we needed to do was look at the signs of the original vectors. But when I'm working in 2D and 3D, the sign isn't enough to give you the direction. As we saw in 2D, you needed like an angle. You needed to say north, 30 degrees west, all right? So I'd like to think of these two vectors in terms of the angle between them. And I notice that when vectors are in the same direction, the angle between them is 0, because you place them tail to tail, the angle is 0. Whereas if the vectors are opposite, the angle between them is 180. And the inspiration for what I'm going to define is what the angle 0 and the angle 180. How can the angle 0 and the angle 180 produce something positive when it's 0 and something negative when it's 180? And if you think about it, what happens when you take cos of 0 degrees? You get exactly 1, but when you take cos of 180 degrees, you get exactly negative 1. So if I think of vector 2 times vector 3, I know I needed to give me 6, so I think of, well, if I take their absolute values, their magnitudes, I get 6, and if I multiply it by cosine of the angle between them, in other words 0, what do I get? I get 6, just as I expect. Whereas if I do the same with vector 2 and vector negative 3, well, what is the magnitude of vector negative 3? It's just 3. So in order to get the negative, I multiply it by cosine of 180, which is negative 1, and I get my negative 6. So this is the, oops, sorry, that's 180 there. This is the inspiration to the definition that I'm going to give, is that when I take cos of 0, I get a positive. When I get cos of 180, I get a negative. Okay, so the way I'm going to define, or one way in which I'm going to define the dot product of two vectors is going to be the magnitude of the first times the magnitude of the second times the cosine of the angle between them. Okay? Now, one reason why this is nice is that if I apply it in one dimension, I just get regular old multiplication, like I showed down here. Okay? That when they're in the same direction, the cosine of the angle between them, which is 0, is going to be 1. And when they're in opposite directions, it's going to be cosine of 180, which is going to be negative 1. And we know that when I multiply two numbers with the same sign, it's positive. Whether both positive or both negative, the angle between them is 0. And when I multiply numbers with opposite signs, the result is negative, the cosine of 180. Okay? Now, this is great. And certainly if I'm dealing, I suppose, with geometrically defined vectors, this is a perfectly good definition, because when a vector is defined geometrically, I know the magnitudes, I can figure out the angle between them. This is easy to calculate, but not very easy to calculate using algebraic vectors. All right, so this is what we call the geometric definition of the dot product. Okay, not the one we necessarily want to work with when we're dealing with algebraic vectors, because if I'm dealing with algebraic vectors, well, it takes a fair bit of work to determine the angle between them. Okay? So the last thing I want to do, remember, when we're working with algebraic vectors, what we want to do is work only with the components. So there is a second definition, an algebraic definition. Okay? And if I let, okay, and I'll do the 2D one, but it's exactly the same in 3D. If I let u be, say, x1, y1, so any two-dimensional vector, and I let v be x2, y2, any other two-dimensional vector, then u dot v, the dot product, is just given by multiplying the individual components and then adding them together. So it's x1, x2 plus y1, y2. Okay? Now, if you wanted to, you could take an example, okay, find the angle between the two vectors, use this definition, okay, then apply that definition to ensure that you do get the same answer either way. So for now, just to save ourselves a bit of time, I'll have to ask you to trust me on this here. But we're going to start to see why this definition is a useful one, or at least one of the reasons. There's a few reasons why this is a useful definition. It's because now I can equate these two expressions because they're both equal to u dot v. So that means that if I take x1, x2 plus y1, y2, that must be equal to magnitude of u times magnitude of v times cosine of theta. Excuse me. Well, wait a minute. Look at what I can do here. Let's say I have two vectors, 2, 1, and 3, -5. Well, remember, the disadvantage of working with algebraic vectors is it's not easy to get their directions, or even the directions with respect to each other. Well, guess what I can now do? And we'll do an example later on. I can now use these two definitions of the dot product being equated to, well, hey, x1 times x2 plus y1 times y2. That's something easy to calculate. The magnitudes, bit of work, but easy to calculate. I can now use the dot product to find the angle between any two vectors. Now, in 2D, you might say, well, I could probably come up with some alternatives. They would take quite a bit longer. But this is going to be important when we get to R3. Okay, because working with angles in 3 dimensions is very difficult, and this is going to allow us to find the angle between vectors much more easily. Okay, so you need to know the definition of this new operation called the dot product. Okay, now the other thing that I want to make sure you notice is that while I am taking the product of 2 vectors, the result is actually a number. Remember I said before, why wasn't I putting vector symbols over those 6's? Because while this may seem strange that I multiply 2 vectors and the result is a scalar, we're going to see that there's a usefulness to this definition. Remember we said when we define something new, this doesn't contradict anything, because when I go to 1 dimension, it still gives me regular multiplication, but it satisfies the other condition in that it's a useful definition. Okay? Now, the only other thing that I will say here, and next week we're going to take a look at some characteristics of this operation, like we looked at, addition, subtraction. Is it commutative or not? Is it distributive? Does it have all those nice characteristics? So we'll take a look at that next week. But there's one characteristic that I want to look at, is that if I have u dot v being equal to the magnitude of u times the magnitude of v times cosine of theta, well, we know that cosine of 0 is a nice number. It gives you 1, and cosine of 180 gives you -1. Okay, but there's another nice angle. What happens when the angle is equal to 90 degrees? Well, cos of 90 is equal to 0. So that means if 2 vectors are perpendicular to each other, then the dot product must be equal to 0, because the angle between them will be 90, and so cos of 90 is always equal to 0. And that is going to be another very useful thing when it comes to the dot product. It allows us to test if 2 algebraic vectors are perpendicular to each other, something that would take a fair bit of time, especially in 3D, to solve using trigonometry, but is going to be very easy using the dot product. All right? So let's keep in mind our 2 definitions, which we can equate when it's useful to do so, and let's look at a couple of questions. And next week we'll go a little more in depth into the dot product. Okay? So let's say I take a look at this here and I wanted to find the angle between the 2 vectors. So let's just remind ourselves that this would be an annoying process. Say 4, 3, there's that angle, and -6, 1, there's that angle. I could, determine these 2 angles and then subtract them from 180. I could connect the tips, use a subtraction, and I guess use maybe a cosine law, both of which would take a fair bit of time. But now, if I use the dot product, it's going to take very little time, because I know that u dot v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between them, and I can calculate everything other than theta very easily. Okay, because on the left-hand side, I'm going to use the algebraic definition of the dot product. And what was the algebraic definition of the dot product? You multiply the x's, you multiply the y's, and you add them together. Okay, so this is just going to be 4 times -6 plus 3 times 1. Okay, and this is equal to, well, the magnitude of u. Very easy to solve. It's just sum of the other 2 squared. So 4 squared plus 3 squared times the magnitude of v. Again, very easy to find. -6 squared plus 1 squared times cosine of theta. And look what we have. The only variable left in the equation is my theta. So let's solve for theta. Okay, so first, what do we have here? We have -24 plus 3, so -21. Let's divide by those, Okay, so what do we have? We have square root of 16 plus 9 is 23. Here we have 36 plus 1 is, 16 plus 9 is not 23, it's 25. Okay, silly error there. So that's why you always go back and look and check. This is definitely 37. And of course, the last step is to take cos inverse of all this. Okay, so let's get our trusty calculator and calculate that here. So we have cos inverse of negative 21 divided by, I'll open up brackets here, so square root of 25 is just 5 times square root of 37. Always better to do all this in one step if you can, and you get 133.7. And when you look at our diagram, it seems to make sense that it's an obtuse angle. Okay, and this is it. Now we have an easy way to find the angle between two vectors with not too much work. Now here in 3D, again, I could do this geometrically. Again, take my two vectors, place them tail to tail, draw this vector here, which is the subtraction, looking for this angle here, do a cosine law, but that would take quite a bit of work. Whereas now, if I use my good old trusty dot product, I can determine this much quicker. So let's start by finding the dot product. So 2 times negative 3 is negative 6. So you see here I go a little faster. Negative 1 times negative 3 is positive 3, so plus 3. And then 4 times 5 is 20, so plus 20. And that's equal to, so what's my magnitude here? So remember, I'm squaring all of these. So 4 plus 1 is 5, plus 16 is 16 is 21. Okay, and here what do we have? We have 9 plus 9 is 18 plus 25. Well, that one I'll just to be sure doing my calculator. 9 plus 9 plus 5 times 5 is 25. So 43 times cos theta. Okay, so theta is going to be equal to cos inverse of, so what do we have here? Negative 6 plus 3 is negative 3 plus 20, so that's 17 over square root of 21, square root of 43. All right, and let's calculate that here. Okay, cos inverse of 17 divided by, open up a bracket, square root of 21 times square root of 43, and we get 55.5 degrees. Okay, much faster than the other alternative we mentioned earlier. All right, so now we see one of the useful reasons for defining dot product as we did. It now allows us to easily determine the angle between two algebraic vectors that would otherwise be a much longer process. All right, so let's take a look at this last example here. So it gives us these two vectors with a variable in it. X, in fact, appears in both vectors, and they tell us that these two vectors are perpendicular. They want us to determine the value of x that make these two vectors perpendicular. Well, this is where we think about what we talked about before. If the vectors are perpendicular, their angle, the angle between them is 90 degrees, and cos of 90 is 0. So that means that u dot v, right off the bat, I can say is equal to 0. And so now, on the left-hand side, I can apply my algebraic definition. So x times x minus 1, okay, plus 2 times 2 is 4, and then plus 5 times negative 2 is negative 10. That's equal to 0. And now look what I have. X squared minus x. 4 minus 10 is negative 6. And I just end up with a quadratic equation, one that's easily solvable by factoring. And in fact, there were two values of x that make these two vectors perpendicular. Okay, x can be equal to 3 or x can be equal to -2. Okay, so two ways to make these vectors perpendicular. All right, so just to recap, this here is we've now defined for the first time a way of taking the product of two vectors, except it turns out that the definition we chose produces as an output a scalar quantity. Okay, but we've seen a couple of examples where it is useful to define it in this way. So very often when you're using the dot product, you're actually using a combination of both the geometric and algebraic definitions, especially if you're determining the angle between the vectors. And one of the nice properties is that if two vectors are perpendicular, their dot product is immediately equal to 0. Now, the only thing I would say beyond this, to give you a sense of where we're going, is why didn't I just call this the product? Okay, I called it the dot product or the scalar product. Well, what that maybe implies to you is that this is not the only way in which we're going to consider products of vectors. Okay, that's it for this week.